In mid-December 2025, with Comet 3I Atlas freshly warmed from its closest pass by the Sun, astronomers turned the James Webb Space Telescope back toward it one more time. And this time, what came back changed the entire scientific picture of what this object actually is. By that point, Webb had already looked at 3I Atlas once, back in August 2025, and found something strange. A coma dominated by carbon dioxide at a ratio far higher than any comet native to our own solar system. But the December observations, combined with data from two other major instruments and published through the first half of 2026, didn't just add one more anomaly to the pile. They assembled into the single most complete picture humanity has ever had of an object that formed around a star other than our own. And the picture that emerged is, in its own way, more remarkable than any invented mystery could be. So let's walk through exactly what Webb found, in order, with every claim traced back to the actual researchers and papers behind it. It's worth understanding why this particular object received this much sustained, coordinated scientific attention in the first place. Because it wasn't guaranteed. Objects passing through our solar system from interstellar space are, by their very nature, rare and unpredictable. Nobody can schedule a telescope years in advance to observe something that hasn't been discovered yet. Every single observation described in this video had to be planned, approved, and executed within an extremely tight window. The brief span of months during which 3I Atlas was close enough, bright enough, and positioned correctly relative to Earth and the Sun for each specific instrument to get a usable look at it. Missing that window for any single observation would have meant missing that particular piece of data forever, since this object will never pass through our solar system again. Comet 3I Atlas was first spotted on July 1st, 2025 by the NASA-funded Atlas Sky Survey Telescope in Chile, and quickly confirmed as only the third interstellar object ever recorded passing through our solar system, after Oumuamua in 2017 and Borisov in 2019. Its hyperbolic trajectory confirmed it wasn't gravitationally bound to the Sun. It came from somewhere else entirely, and it would leave again forever once its short visit was over. Each of those three known interstellar visitors turned out to be genuinely different from the other two, which matters for understanding why 3I Atlas specifically generated this much research interest. Oumuamua in 2017 showed almost no detectable gas activity at all, leaving researchers with frustratingly little material to actually analyze before it faded from view. Borisov in 2019 behaved much more like an ordinary solar system comet, chemically unremarkable by comparison. 3I Atlas turned out to be the first of the three to combine strong, sustained, well-measured activity with genuinely unusual chemistry, giving instrument teams, for the first time with this class of object, something substantial enough to actually study in this kind of depth. The first major scientific result came in August 2025, when astronomers pointed Webb's near-infrared spectrograph, called NIR-SPEC, at the comet while it was still three astronomical units from the Sun. According to research led by NASA astrochemist Martin Cordner of NASA's Goddard Space Flight Center, that observation revealed a coma, the gas cloud surrounding a comet's icy nucleus, with a carbon dioxide to water ratio measured at 6 to 1, roughly 18 times higher than what's typical for a comet at that same distance from the Sun, based on decades of data from comets native to our own solar system. That single measurement on its own was already one of the most unusual chemical signatures ever recorded in any comet. To understand why that ratio matters so much, it helps to remember how comets typically behave as they warm up near a star. Different ices trapped inside a comet's nucleus turn to gas at different temperatures. Water needs considerably more heat than carbon dioxide does before it will sublimate directly from solid to gas. At any given distance from the Sun, decades of studying solar system comets have given astronomers a very reliable sense of roughly what proportion of each gas should be boiling off. 3I Atlas's measurement didn't just sit slightly outside that expected range, it sat far enough outside it that researchers described the result as statistically significant, at a level equivalent to about 4.5 standard deviations from the norm, a threshold most scientific fields treat as a genuinely serious, not easily dismissed anomaly, rather than routine variation. Then, in December 2025, as 3I Atlas moved away from the Sun and its ancient ice, freshly heated by solar exposure, converted into a particularly bright coma of outgassing material, Webb turned a second instrument toward it, the mid-infrared instrument, known as MIRI. According to research led by Caltech's Matthew Belyakov, MIRI observed the comet on December 15th and 16th, 2025, at a distance of about 20 astronomical units from the Sun, and then again on December 27th at roughly 54 astronomical units, after a technical issue with guide star acquisition, forced part of the initial observation to be repeated. That repeat turned out to be scientifically fortunate. What MIRI found was methane, and this was the first time this specific gas had ever been directly detected on any interstellar object. Neither Oumuamua nor Borisov had shown any trace of it. According to Belyakov's team, the methane production rate measured on December 15th and 16th came in at approximately 4, 2 times 10 to the 26th molecules per second, dropping slightly to about 2, 3 times 10 to the 26th by December 27th, and crucially, the ratio of methane to water was considerably higher than what's typically seen in comets from our own solar system. It's worth pausing on those production rate numbers for a moment, because a figure like 4, 2 times 10 to the 26th molecules per second, is genuinely difficult to picture in everyday terms. That's over 400 trillion individual methane molecules escaping from the comet's nucleus every single second, continuously, for as long as that outgassing period lasted. And this was happening on an object roughly 205 million miles from the Sun, meaning every one of those molecules, and the faint infrared signature they produced, had to travel that entire distance before Webb's instruments could detect them at all. The fact that MIRI could measure a production rate this precisely from a comet this far away is itself a demonstration of just how sensitive this particular instrument actually is. Here's where the story gets genuinely interesting rather than simply strange, because the research team didn't just report the anomaly, they explained the timing behind it. Methane is one of the most volatile substances found in cometary ice, meaning it should, in principle, boil off relatively easily even with modest heating. Its detection only showing up after the comet's closest approach to the Sun, rather than during the buildup toward perihelion, initially seems backward. But Belyakov's team proposed a specific, testable mechanism. The methane likely sat buried deeper within the comet's nucleus, below a surface layer that had already lost its more easily accessible volatile ices to space long before this particular pass through the inner solar system. It simply took time for the Sun's heat to conduct down through that processed outer crust and finally reach the buried methane deep enough to release it. That explanation connects directly back to the same ancient radiation-processed history that shows up throughout this entire object story. A surface that's spent 10 billion years drifting through interstellar space, continuously exposed to galactic cosmic radiation, would be expected to develop exactly this kind of layered structure. An outer crust chemically altered and depleted of its most volatile compounds over unimaginable timescales, with fresher, more volatile material like methane preserved only deeper inside, protected from that same radiation exposure by the layers above it. Solar heating, arriving for the first time in billions of years, would naturally need time to work its way down through that crust before reaching material that hadn't been touched by starlight since before our own sun existed. That single piece of reasoning matters enormously, because it's a direct rebuttal to the idea that unexplained and unnatural mean the same thing. This delayed methane release is exactly the kind of layered, physically grounded explanation that real planetary science produces when it encounters something new. Not a shrug, and not a leap to anything exotic, but a specific, checkable hypothesis about heat conduction through an ancient, radiation-weathered surface. The same MIRI observations also tracked something else worth noting directly. Water production from the comet dropped sharply between the December 16th and December 27th observations. According to the research team's own explanation, that's because 3I Atlas had, by that point, crossed what's called the water snow line, the specific distance from the Sun, around 5 astronomical units, beyond which temperatures become cold enough that water ice stays frozen rather than sublimating into gas. Watching that transition happen in real time, on an object from another star system entirely, gave researchers a genuinely rare, direct look at exactly how a comet's chemistry changes as it crosses one of these well-understood physical thresholds. Around the same period, a completely separate instrument added its own layer to the picture. NASA's SPHEREx mission, an infrared observatory designed specifically to map chemical signatures across the sky, re-observed 3I Atlas in December 2025, according to research led by MC Liss of Johns Hopkins University's Applied Physics Laboratory. Compared to SPHEREx's earlier pre-perihelion look in August 2025, the December data showed a considerably more active object, with clearly detected water, carbon monoxide, carbon dioxide, the cyanogen radical CN, refractory dust, and a broad organic carbon-hydrogen feature spanning wavelengths from about 2 to 3, 6 microns. That last detail is worth sitting with specifically because it's not simply confirming the presence of one isolated molecule. A broad organic feature like that reflects a genuinely complex mixture of carbon-based compounds, exactly the kind of chemistry astrobiologists care about when studying how the raw ingredients for life-related chemistry get built and distributed across a galaxy. It's worth being precise about what that broad organic feature actually means scientifically, because it's a genuinely different kind of finding than a single, sharp detection line. When an instrument picks up one isolated spectral line, It's typically identifying one specific molecule with high confidence. A broad feature spanning a range of wavelengths, by contrast, usually indicates a complex mixture of several different, closely related carbon-hydrogen compounds overlapping together, rather than one single, cleanly identifiable substance. Distinguishing exactly which specific organic molecules make up that broad SPHEREx signature is itself an active area of ongoing analysis, separate from the sharper, more specific methane detection MIRI achieved. Together, the two results paint a picture of a genuinely rich, complex organic chemistry aboard this comet, observed at two different levels of specificity by two entirely different instruments. Separately, and using an entirely different observatory on the ground, researchers led by astronomer Cyril Aupetom of the University of Edinburgh used the European Southern Observatory's Very Large Telescope to analyze 3I Atlas's carbon and nitrogen isotopes, specifically as they appear in the chemical cyanide. According to Stephanie Millam of NASA Goddard, a co-author on the complementary web research, finding these particular rare isotopes is scientifically fascinating in its own right, but the bigger picture, in her own words, is what they reveal about the possibilities of prebiotic chemistry occurring elsewhere in the galaxy, entirely independent of anything happening here on Earth. Isotopes are, in effect, another chemical fingerprint, similar in spirit to the deuterium to hydrogen ratio Webb measured, but focused on carbon and nitrogen instead of hydrogen. Different isotopes of the same element form in slightly different proportions, depending on the specific physical conditions present when the surrounding gas and dust originally condensed, meaning a precise isotope measurement can help pin down details about a comet's birthplace that a simple chemical inventory alone can't fully capture. Having the VLT's ground-based isotope analysis available alongside Webb's own space-based measurements gave researchers two genuinely independent methods converging on the same underlying question: what kind of environment actually produced this object? And how does that environment compare to the one that built our own solar system? All of these separate threads, Webb's NER spec and MIRI data, SPHEREx's independent chemical mapping, and the VLT's isotope analysis, came together in a single major paper led once again by Martin Cordner, published on June 22, 2026, in the peer-reviewed journal Nature. That paper is the real, sourced answer to what the truth about 3I Atlas actually looks like, and it's worth walking through directly. According to that Nature paper, Webb's measurements of specific chemical ratios, including the balance between regular hydrogen and deuterium, sometimes called heavy hydrogen, pointed toward an age for this comet of somewhere between 10 and 12 billion years. To put that in perspective, our own solar system is roughly 6 billion years old. This object had likely already existed, drifting through the galaxy for more than twice as long as the Sun and Earth have existed, before it ever crossed paths with us. Cordner himself described the significance of the moment directly. This was, in his words, a unique opportunity to study an ancient object from the distant galaxy, probably predating our own sun and solar system entirely, giving researchers, as he put it, direct insight into that distant time and place, while simultaneously learning something about how unusual our own solar system may be by comparison. The paper goes further still, connecting the comet's specific trajectory through the solar system to a particular population of stars within our own galaxy. According to that research, and consistent with earlier analysis of 3I Atlas's steep, unusual approach path, the comet's motion is consistent with an origin among the Milky Way's thick disk, an older, more chemically primitive population of stars, generally lower in the heavier elements built up by later generations of stellar explosions, and structurally puffier and less flattened than the thin disk our own sun belongs to. If that connection holds, 3I Atlas isn't simply old in years. It's a direct chemical sample from a fundamentally different era and population within our galaxy's own history. A comet built from raw material that predates the specific conditions that eventually produced our sun, our planets, and every comet native to our own solar neighborhood. It's worth explaining what actually separates a thin disk star system from a thick disk one, because the distinction carries real scientific weight, rather than just sounding impressive. Our galaxy built up its heavier elements gradually, over billions of years, as successive generations of massive stars lived, died, and exploded as supernovae, seeding the surrounding gas with progressively more carbon, oxygen, iron, and other elements beyond hydrogen and helium. Stars that formed earlier in this process, from less enriched material, tend to belong to the thick disk, older, chemically simpler, and orbiting the galaxy's center on more inclined, less tightly organized paths. Stars that formed later, including our own sun, benefited from all that earlier chemical enrichment, and tend to sit in the flatter, younger, more metal-rich, thin disk. If 3I Atlas really did form around a thick disk star, its raw material would have been assembled under measurably different chemical conditions than anything that built our own solar system, which lines up directly with the unusual carbon dioxide ratio, the unexpected methane behavior, and the specific isotope measurements researchers kept finding throughout this entire investigation. That's the real headline hiding underneath a title like The Truth About 3I Atlas. Not a hidden threat and not a concealed signal, but a directly measured, peer-reviewed, published age and origin for an object that arrived from outside our solar system, confirmed through multiple independent instruments, cross-checked against multiple independent teams, and now sitting in the permanent scientific record in one of the most rigorously reviewed journals in the world. It's worth being completely clear about the other side of this story too, because the truth also includes ruling things out, not just confirming things in. A dedicated research effort specifically focused on searching for technosignatures, potential evidence of artificial origin, across all 3 known interstellar objects concluded, in the researchers' own words, that the rapidly growing suite of observations for 3I Atlas strongly supports the conclusion that it is a comet, and that to date, there is no credible evidence that any of the 3 interstellar objects detected so far are anything other than natural. That's not a hedge, and it's not a partial answer. That's the direct published conclusion of researchers who specifically set out to test the artificial origin hypothesis using real instruments and reported their results plainly. That conclusion sits alongside and is reinforced by the earlier radio searches conducted by the SETI Institute using the Allen Telescope Array, and separately by the Breakthrough Listen program using the Green Bank Telescope, both scanning 3I Atlas across wide ranges of radio frequency, and both coming back with the same result. No transmission, no artificial signal, nothing beyond ordinary interference already traced back to sources here on Earth. 2 independent radio searches, 1 dedicated technosignature research effort, and now a peer-reviewed Nature paper laying out the comet's actual chemical age and galactic origin. That's 4 separate independent lines of evidence from 4 separate research efforts, all converging on the same picture. It's worth explaining briefly what actually goes into a technosignature search like this, since the term can sound vague if you've never seen how it's actually done. Researchers systematically look for any signal, emission, or physical behavior that has no plausible natural explanation, but that would make sense if the object were engineered. Narrowband radio transmissions, precisely regular timing patterns unlike anything natural outgassing produces, or materials that simply couldn't form through known astrophysical processes. Every one of those specific tests was run against 3I Atlas directly, using real data, by researchers who published their exact methodology alongside their results specifically so other scientists could double-check their work. Coming back empty, after that level of specific, deliberate testing, is a meaningfully stronger result than simply never having looked in the first place. So, what is the actual full truth about 3I Atlas once you put every piece of real, published research together? It's a comet, confirmed through multiple independent chemical, spectroscopic, and radio investigations. It very likely formed somewhere between 10 and 12 billion years ago, quite possibly around a star belonging to the galaxy's older thick-disk population, long before our own sun ever ignited. Its ice contains an unusually high ratio of carbon dioxide to water, a delayed release of buried methane unlike anything seen in either of the 2 previous interstellar visitors, and a genuinely complex mixture of organic carbon compounds worth studying specifically for what they reveal about the raw chemical ingredients available for life-related processes elsewhere in the galaxy. And across every serious search conducted for anything artificial about it, the answer has come back the same way every single time. Nothing that's not a disappointing answer. It's arguably a far more interesting one than any invented alternative because it means humanity got a direct, detailed chemical readout from a physical object that predates our own solar system by billions of years. An actual tangible sample of conditions from a different era and possibly a different population of stars entirely, delivered not through speculation, but through carbon dioxide ratios, deuterium measurements, methane release timing, and organic carbon signatures, all captured by real instruments, published under real names in a real peer-reviewed journal that any scientist in the world can go check. Think about what that actually represents, stepping back from the individual measurements for a moment. Every planet, every comet, every asteroid native to our own solar system carries a chemical signature shaped by the same roughly 6 billion year history. The same starting materials, the same sequence of events, the same relatively narrow range of formation conditions. 3I Atlas broke that pattern entirely, arriving with a chemical signature built somewhere else, under different conditions, over a time span more than twice as long as our entire solar system has existed. Studying it isn't just adding one more comet to an existing catalog. It's the closest thing to physically sampling another star system that current technology allows, without ever having to leave our own. If you want to verify any of this yourself, here's exactly where to look. Search Cordner 2026, Nature 3I Atlas for the June 22nd, 2026 paper, laying out the comet's age and thick disk origin directly. Search Belyakov 2026, 3I Atlas Methane MIRI for the paper detailing the first ever methane detection on an interstellar object and its delayed release explanation. Search SPHEREx 3I Atlas December 2025 for the independent chemical mapping that complemented Webb's findings. And search Technosignature Interstellar Objects 2025 for the direct published conclusion ruling out artificial origin across all 3 known interstellar visitors. Every one of those searches leads to a real paper, a real named lead author, and a real publication date, not a vague reference to unnamed officials or unconfirmed leaks. None of those papers sit behind a paywall you'd need special credentials to get past. Nature's coverage was mirrored directly by NASA and ESA's own public science pages. The MIRI and SPHEREx results are discussed openly in mainstream science journalism, and the Technosignature paper is freely available on ARC-Show for anyone who wants to read the full methodology rather than just the summary. Checking a claim like this takes about the same amount of time as watching this video a second time. There's something worth sitting with in just how much verified, published research accumulated around a single object in under a year. From first discovery in July 2025 to a landmark Nature paper in June 2026, 3I Atlas generated results from NIR SPEC, MIRI, SPHEREx, the Very Large Telescope, the Allen Telescope Array, and the Green Bank Telescope. 6 separate major instruments run by teams across multiple countries and institutions, all independently studying the same object during the single, unrepeatable window it happened to be passing through our solar system. That level of coordinated, rapid scientific attention focused on one specific object is itself a genuinely rare event in the history of astronomy. Consider what coordinating that many independent instruments actually requires in practice. Each of those 6 facilities operates under its own institutional review process, its own scheduling constraints, and its own team of specialists. Yet within the space of less than a year, all 6 ended up pointed at the same object, at carefully chosen moments, timed around its changing distance from the Sun, producing results that were then written up, peer-reviewed, and published in ways that let each team's findings reinforce and cross-check the others. That kind of rapid, informal coordination across so many independent institutions doesn't happen for most objects astronomers study. It happened here specifically because everyone involved recognized correctly that this exact opportunity would never come again. And now that window has closed. 3I Atlas has already passed its closest approach to Jupiter in March 2026 and is heading back out of the solar system permanently, fading from view as the distance between it and every telescope studying it continues to grow. Whatever else researchers eventually learn about this object will have to come entirely from the data already collected during this one visit, because there won't be a second chance to look again. The window during which humanity could point real instruments at this specific piece of another star system has now closed permanently, making every measurement described in this video part of a finite, unrepeatable dataset that scientists will keep analyzing for years to come. That's the actual truth this story was always building toward. Not a secret being kept from the public, but an extraordinarily rare, extraordinarily well-documented scientific opportunity, seized in real time by multiple research teams working independently and then publishing their results openly for anyone willing to go check the sources directly. If you want the real, sourced version of space stories like this as new research continues to come out, subscribe. Because 3I Atlas's data will likely keep generating new papers and new analysis for years, even though the comet itself is already gone for good. And if you've heard another claim about this object that sounded a little too dramatic to check, drop it in the comments, and I'll tell you exactly what the actual published research says. There's a fitting symmetry to how this particular story ends. An object that spent somewhere between 10 and 12 billion years drifting alone through the space between stars, carrying chemistry from an era that predates our own solar system, happened to pass close enough at exactly the right moment in human technological history for 6 major instruments across multiple countries to study it in genuine, unprecedented detail. And then it kept moving, exactly as it always would have, indifferent to any of the attention it received, heading back out into the same interstellar darkness it came from, carrying its true origin with it, either way, whether or not anyone had been watching.